Come on, my dears, let us proceed further in chapter number 2. Today we will study the application of Phasors method for finding resultant function out of more than one harmonic functions. If you require to add more than one harmonic functions, and if you require to find out resultant harmonic function, how would you do that using Phasors method? That we will study. Okay, fine. Suppose we have two harmonic functions, I1 equals to I1m cos of omega t plus delta 1, I2 equals to I2m cos of omega t plus delta 2. Why are they called harmonic functions? Because in mathematics, sine and cosine, both the functions are called harmonic functions. That's why these functions are called harmonic functions, because they involve cosine function. Just give me identification of each quantity. What is I1? It is instantaneous value of first function at time t. What is I1m? It is maximum value of first function. Omega is angular frequency, t is given time, delta 1 is initial phase of first function. What about I2? It is instantaneous value of second function. I2m is maximum value of second function. What about omega? Angular frequency, t is given time, delta 2 is initial phase of second function. Correct? First of all, you do one thing, you represent both the functions by respective phasors. You know, phasor is a vector which represents the harmonic oscillations, correct? And while representing a given harmonic function by a phasor, you know, you have to draw a vector having length equal to magnitude of a given vector, I mean maximum value of that function, and then you should draw that vector in such a manner that angle made by that vector with a positive x-axis should be equal to phase of the given harmonic function, and component of that vector along positive x-axis or positive y-axis should be equal to instantaneous value of that harmonic function. I am showing you how to do that. To represent first harmonic function, I have drawn first phasor. It is from O to A. Vector OA represents first harmonic function. Fine. Now that vector OA has magnitude this much equal to OA, which is equal to, maximum value of first harmonic function I1m. Angle made by that vector with x-axis is angle AOX. It should be equal to phase of first harmonic function, that is omega t plus delta 1. Omega t plus delta 1. Correct? And if you draw a perpendicular from head, then you will find this much component, and this much component will give you instantaneous value of that harmonic function. Why? Because mathematically, if you think from trigonometry point of view, component of I1m adjacent to omega t plus delta 1, I repeat, component of I1m adjacent to omega t plus delta 1, what is it? I1m into cos of omega t plus delta 1, which is nothing but I1. That's why I written here I1. Correct? Now represent second harmonic function by second phasor, and it is vector AP. Vector AP. Correct? Now tell me, length of this vector is equal to maximum value of second harmonic function, that is equal to I2m. Correct? I2m. Fine. Now angle made by this vector with positive x-axis should be equal to phase of second harmonic function. and it is omega t plus delta 2. Here it is. This angle is omega t plus delta 2. Okay. Now, let us find out component of this vector on x axis. For that purpose, you can draw perpendiculars from tail and also from head. When you draw two perpendiculars, this much distance would give you component of this vector along x axis. It is component of I2m adjacent to omega t plus delta 2. It should be I2m cos of omega t plus delta 2, and I2m cos of omega t plus delta 2 is nothing but I2. That's why here I have written I2. Correct? And now tell me, if you want to add these two functions, correct, then how would you write that addition? Come on. Resultant harmonic function is suppose I, that should be equal to I1 plus I2. I1 plus I2. Fine. So I equals to I1 plus I2. So if you make addition of these two, I1 and I2, then the value is I, which is this much. Okay, fine. Now tell me, what have you done here? You have made vector addition of these two vectors, vector OA plus vector AP. Phasor plus phasor will give you resultant phasor. It is from O to P. So vector OP gives you resultant phasor. And tell me, what is the length of phasor? Equal to maximum value of given harmonic function. Here this much length will give me maximum value of resultant harmonic function. Maximum value of resultant harmonic function. Fine. Angle made by resultant phasor with x-axis, that is angle POX, will give you phase of resultant harmonic function. Phase of resultant harmonic function, let it be phi. And if you draw perpendicular from head P on x-axis, then this much component OQ will give you instantaneous value of resultant harmonic function at time t. Got it? So this is how we can represent resultant harmonic function by this resultant phasor. But now if you require to find out value of Im, then what is the formula for that? Formula is this: Im equals to under root of I1m square plus I2m square plus 2I1m I2m cos delta. Could you remember? Do you find this formula similar to some other formula you had studied in 11th standard? Vector A plus vector B, if it is equal to vector R, then what was the magnitude of resultant vector R? It was R equals to under root of A square plus B square plus 2AB cos theta. What was theta? It was angle between vector A and vector B. So here let us find out angle between these two vectors. Angle between this vector and this vector. How to find that angle? I am showing you. Just extend this vector in the same direction. Okay? Then these two are corresponding angles. They will be equal. If this is omega t plus delta 1, this also will be omega t plus delta 1. Correct? Fine. This much angle is omega t plus delta 2. This much angle is omega t plus delta 1. Suppose I want to find out this angle. Then bigger minus smaller. Bigger minus smaller. Take this minus this. If you take this minus this, then omega t minus omega t will cancel. Delta 2 minus delta 1. Here it is. Delta 2 minus delta 1. Correct? Phase minus phase. Phase minus phase will give you phase difference. Phase difference. And let it be delta. So delta is phase difference between two given harmonic functions. And now tell me, in terms of I1m, I2m and delta, what is the formula of Im? Formula is this: Im equals to under root of I1m square plus I2m square plus 2 I1m I2m cos delta. You know the formula, capital R equals to under root of a square plus b square plus 2ab cos theta. Instead of a, you just write I1m. Instead of b, you just write I2m. Instead of theta, you write delta, and instead of r, you just write Im. Correct? My dears, not necessary that this Phasors method is useful only for cosine function, not necessary. You may have here sine function. Then also resultant function can be found out using this Phasors method. The only difference at that time, instead of taking components on x-axis, you should take components on y-axis. Correct? There also Phasors method is applicable. Fine. Now, let us consider 3 AC circuits, and then using Phasors method, let us find out phase difference between voltage and current. Very simple. First of all, we take only resistor, and recall the formula of phase difference between voltage and current. It was delta equals to tan inverse of XL minus XC upon R. Now tell me, when you are talking about only resistance, then these two components are not there. If inductor is not there, then XL is 0. If capacitor is not there, then XC is 0. When these two values are 0, then 0 upon R will be 0, and tan inverse of 0 will give you 0. Tan inverse of 0 is 0. So delta will be 0. When delta is 0, meaning thereby there is no phase difference between voltage and current, meaning thereby current phasor and voltage phasor should have same direction, then only angle between them would be 0. And normally current phasor we just draw on positive x-axis, then in the same direction you should indicate the voltage phasor also. So you can see voltage phasor and current phasor, they are in same direction, that's why phase difference between them is 0. Correct? But this is true only in that AC circuit in which only resistor is present. Okay? We go for only inductor. If only inductor is there, then what will happen? Come on, only inductor is there. So X is 0, R is 0. Positive number divided by 0 will give you plus infinity, and tan inverse of plus infinity, so you will get delta equals to plus pi by 2 radian. Delta equals to plus pi by 2 radian. Fine. Phase difference between voltage and current is plus pi by 2 radian. Current phasor we always indicate on positive x-axis. So this is positive x-axis. This is positive x-axis, and here voltage is leading in phase. If voltage is leading in phase, I told you whenever delta is positive, voltage is leading ahead in phase. At that time voltage phasor should be shown higher. Come on. Voltage phasor you should show at present along positive axis such that this angle should become plus pi by 2 radian. In first quadrant that angle is positive. Had it been negative, we could have shown it in the fourth quadrant. Fine. Now this angle is right now delta equals to plus pi by 2 radian. Fine. Now think of that circuit in which only capacitor is present. Okay? Fine. Now tell me, if only capacitor is there, then these two values are 0. So negative number divided by 0 will be minus infinity, and tan inverse of minus infinity, so delta will be minus pi by 2 radian. And when delta is minus pi by 2 radian, as usual you should show current phasor along positive x-axis, but whenever delta is negative, voltage is lagging behind in phase. If voltage is lagging behind in phase, then its phasor you should show downwards along negative y-axis. That's why this angle in fourth quadrant will be minus pi by 2 radian. Got it? This is how using phasor diagram we can relate the phase relationship between voltage and current. Correct? Now, how to apply Phasors method for series RLC AC circuit? Look, Phasors method Phasors method for series RLC AC circuit. Look, Phasors method for series RLC AC circuit. In this chapter, in the very first theory, which was very long, at the end of that whole long theory, we had obtained the formula of phase difference between current and voltage. It was tan inverse of XL minus XC upon R. Now, same formula here we will obtain using very short method, and that short method is Phasors method. How to get it? I am showing you. Consider one series RLC AC circuit in which series combination of resistor, inductor and capacitor is connected across an AC source. Fine. What is the alternating voltage offered by AC source? V equals to Vm cos omega t. Fine. Now tell me, if maximum current passing through this circuit is Im, at that time let us find out potential differences across different components. Potential difference across this resistance would be Im into R. But because current is maximum, naturally voltage also will be maximum. Voltage across resistance, so we write VR. But because it is maximum, we are writing VRM. In textbook, they have not written this M, they have written simply VR, but it is not simply voltage, it is maximum voltage. So I am putting here M. The way they have put here I1M. I1M means maximum value of first harmonic function. The way they are putting here M for maximum, similarly here also I am putting M for maximum. So this is the maximum voltage across the resistor, it is Im into R. Similarly, maximum voltage across inductor, it is maximum current into magnitude of inductive reactance, which is XL. Similarly, maximum voltage across capacitor is maximum current into magnitude of capacitive reactance, that is XC. Fine. Now tell me, let us find out maximum value of resultant voltage using phasor diagram. For resistor, you know, voltage phasor points in the same direction of current phasor. Both of them point in the along positive x-axis. So for voltage, for maximum voltage across resistor, you should draw corresponding phasor along positive x-axis, correct? For inductor, voltage phasor should be shown common along positive y-axis. So maximum voltage across inductor is shown by a phasor along positive y-axis. Then voltage phasor for capacitor should be shown vertically downwards, that is along negative y-axis. That's why maximum voltage across capacitor I have shown by a phasor along negative y-axis. Suppose, see, these two Im are same, Im same, but suppose XL is greater than XC. XL is greater than XC. When XL is greater than XC, naturally VLM will be greater than VCM. If VLM is greater than VCM, then you can subtract the smaller value from this bigger value, then it will be VLM minus VCM. VLM minus VCM. Fine. Now tell me, VLM minus VCM, so it will be, say, this much. Okay, fine. This minus this, suppose I am getting this much, and then from that point onwards you should draw horizontal line, and from this point onwards we should draw vertical line, and where both the line segments intersect, that point you should join with origin, and then you should find out such a length, and this length will give you maximum value of resultant voltage. Maximum value of resultant voltage. And now this phasor I have just shifted from here to here, from here to here, correct? Now this is the voltage phasor, which is how much? VLM minus VCM. I just remind In textbook, they have not written this M, but yet they are maximum voltages only. Fine. Now tell me, this is one phasor, this is another phasor. Phasor plus phasor will give you resultant phasor, but that resultant phasor appears before in front of right angle. Come on, opposite to right angle, what is it? Hypotenuse. And for this right angle triangle, what is the measurement of hypotenuse? According to Pythagoras theorem, measurement of hypotenuse will be equal to square root of summation of squares of remaining two perpendicular sides, that is under root of VRM square plus VLM minus VCM whole square. Again, Vm will be equal to under root of VRM square plus VLM minus VCM whole square. Fine. What is VRM square from here? Square of this will be equal to square of this. Come on, Im square R square. Here it is, Im square R square, correct? What is VLM? VLM is Im into XL, Im into XL, minus, what is VCM? VCM is Im into XC, come on, Im into XC, whole square. Now tell me, can you take Im common? Yes, we can take, but because here it is square, then only after making it squared, you can take it out. So here you can think of Im square, but then this Im square and this Im square, when you take out, after taking square root, you can bring it out. What is square root of Im square? It is only Im. Inside the bracket, it will be under root of, come on, R square plus XL minus XC whole square. XL minus XC whole square. Got it? You just find out Im from here. If you find out Im, it will be Vm upon this. Vm upon under root of R square plus XL minus XC whole square. Now, according to Ohm's law, current should be equal to voltage upon resistance. Current should be equal to voltage upon resistance. Here it is maximum current, here maximum voltage, and here it should be resistance of AC circuit, which is called magnitude of complex impedance, shown by symbol mod Z. So this right hand side you may write this way, Vm upon mod Z, Vm upon mod Z. Now if you compare, mod Z will be this much. Mod Z will be, come on, under root of R square plus XL minus XC whole square. Tell me, what is this? Formula for magnitude of complex impedance. Same formula we had obtained in this chapter in first theory, but that method was very long. Here this is very short method. And now, in this right angle triangle, suppose I want to take tan delta. What is tan delta? First of all, tell me why this much angle is delta? Because in this direction there is a current phasor along positive x-axis. In this direction there is a resultant voltage phasor. Angle between voltage phasor and current phasor should be taken as delta. That's why I have given the symbol here, delta. Find out tan delta. It is opposite upon adjacent. Opposite is this much. VLM minus VCM upon adjacent is VRM. Come on, tan delta equals to, opposite is VLM minus VCM, upon adjacent is VRM. What is VLM? Come on, VLM is how much? Im into XL. VLM is Im into XL minus VCM. VCM is how much? Im into XC. Come on, Im into XC. Upon VRM. Come on, VRM is how much? Im into R. Come on, Im into R. Can you take Im common from numerator? Yes. And that Im and this Im will be getting cancelled, giving you XL minus XC upon R. XL minus XC upon R. If tan delta is XL minus XC upon R, what is delta? Delta would be tan inverse of XL minus XC upon R. Delta equals to tan inverse of XL minus XC upon R. Correct? This gives you phase difference between voltage and current. Got it? Now we discuss very important circuit called LC circuit, or sometimes we call it parallel LC circuit. Whether you say parallel LC circuit or only LC circuit, it is one and same. that LC circuit is this. Tell me, what are connected? One inductor of inductance L and one capacitor of capacitance C are connected together. This gives you LC circuit. But suppose this capacitor before connecting with inductor was fully charged, and charge on capacitor we take initially Q0. When the charge on capacitor was Q0, at that time it was connected with this inductor, and that moment of connection is supposed t equal to 0. So at time t equal to 0, there is a maximum charge on the capacitor, let it be Q0, fine. Now when you connect it across inductor, at the same moment t equal to 0, there is no current through this inductor, but later on current starts flowing from positive to negative this way. In this direction current starts flowing, fine. If current is flowing in this direction, then electrons are flowing in opposite direction. Electrons are transferred from this negatively charged plate to this positively charged plate this way. Tell me, as more and more electrons are getting transferred from here on this plate, negative charge will decrease, and those electrons will simply neutralize some of the positive charge here. So positive charge on this plate will decrease. I mean to say, charge on this capacitor goes on decreasing, fine. When charge is decreasing, we say capacitor is discharging, So naturally, after some time, charge on this capacitor will be less than Q0, but exactly how much, that is what we have to find out, fine. Now when you connected this capacitor with this inductor at time t equal to 0, there was no current through this inductor, but after some time, say at the end of t time, there is some current through the inductor, let it be capital I. What is that capital I value? That is also we want to find out. In short, at the end of t time, we want charge on this capacitor and we want current through this inductor, fine. At time t, current passing through inductor is suppose I, and time rate of change of current, let it be di by dt, fine. Now according to Kirchhoff's second law, here summation of voltages obtained across capacitor and inductor should be equal to applied voltage. There is no battery connected, there is no applied voltage, so applied voltage is 0. And voltage across inductor I am taking VL, voltage across capacitor I am taking VC. What is VL? Magnitude of self-induced EMF, which is L into di by dt, plus VC, by formula it is Q by C, should be equal to 0. Come on, L as it is, don't you know? I equals to dq by dt, I equals to dq by dt. When I equals to dq by dt, if you take d by dt on both the sides, then di by dt will be equal to d2q by dt square. Here it is. Di by dt can be replaced by d2q upon dt square plus q upon c as it is, that equals to 0. Transfer this part. When you transfer from plus, it will become minus. Divide each term by capital L. If you do that here, it will give you d2q upon dt square, and when you divide by L here, minus q upon LC, fine. This equation is called differential equation of given LC circuit. I repeat, differential equation of given LC circuit. Now this differential equation is quite similar or analogous to differential equation of pure simple harmonic motion, which you had studied in second semester, and it was this: d2y upon dt square equals to minus omega 0 square y. I repeat, d2y upon dt square equals to minus omega 0 square y. Fine. Now just match these two. If you match, then y, you know displacement is similar to charge. Come on, minus as it is. Come on, displacement is similar to charge. And don't you know formula of omega 0? 1 upon under root LC. 1 upon under root LC. If you take square, omega 0 square is equal to 1 upon LC. 1 upon LC. I mean to say, this differential equation is quite similar to this. And now, what was the solution of this differential equation which you had studied in second semester? It was this: y equals to a sine omega 0 t plus 5. Their capital A was amplitude, which is nothing but maximum displacement, So I am putting the symbol Ym. Now similar to this, here also you can write solution of this differential equation as q equals to qm sine of omega 0 t plus phi. What is this qm? Maximum value of this charge. What is omega 0? Angular frequency. And what is this phi? Initial phase. Fine. Now tell me, here the maximum charge, it was the charge on this capacitor at time t equal to 0. Because at time t equal to 0, fully charged capacitor was connected to this inductor. So at that time, whatever was the charge present on capacitor, that was none but maximum, it is Q0. So we know that this maximum charge is nothing but Q0. So in place of Qm, we can write Q0. In place of Qm, we can write Q0 sine of omega 0 t plus 5 as it is. So this gives you expression of charge on a capacitor at the end of t time after connecting it with an inductor. Fine. At time t equal to 0, just put it here. At time t equal to 0, q equals to q0. At time t equal to 0, come on, q equals to q0. Put q equals to q0, correct? And when you put t equal to 0 here, this part will be 0. Q0 sine of phi. Come on, Q0 sine of phi. And now Q0 will cancel. Sine phi equals to 1. When sine phi is 1, naturally phi is pi by 2 radian. Put that value of phi here. Come on. Q equals to Q0 sine of omega 0 t plus pi by 2. Come on, phi value is pi by 2. But don't you know, sine of pi by 2 plus theta is nothing but cos theta. So here sine of pi by 2 plus omega 0 t will be cos of omega 0 t. This Q0 as it is. So ultimately Q equals to Q0 cos of omega 0 t. Q equals to Q0 cos of omega 0 t. This gives you, come on, expression of charge on capacitor at the end of t time. But at the end of same t time, what is the current through the inductor? Let us find out. You know, I equals to dq by dt, that is d by dt of q. Come on, d by dt of q. What is q? Q equals to q0 cos of omega 0 t. Come on, q equals to q0 cos of omega 0 t. Because q0 is constant, can be taken out. And derivative of cos is minus sign. Derivative of cos is minus sign of omega 0 t. Derivative of omega 0 t with respect to t is only omega 0. And now rearrange it properly. Minus q0 omega 0 sine of omega 0 t. Minus q0 omega 0 sine of omega 0 t. This gives you formula of current passing through inductor at the end of t time. Now in textbook they have not plotted any graph. Let us plot these two graphs, things will be more clear. I want to plot a graph of q versus t. Here it is, q versus t, correct? And that graph is like a graph of cosine function, because here in the formula we find cosine function. And you know, cosine function graph starts from maximum and then after it changes periodically. Fine. What about graph of I versus t? It will be, come on, inverted graph of sine function, because it is here negative sign. It indicates inverted graph of sine function. Then inverted graph of sine function, come on, it is like this, correct? Fine. This is the graph of I versus t. Because it is inverted graph of sine function, you should first of all show this part, that is crest and then trough. This is trough and then crest, okay? If you place here t equal to 0, then sine 0 is 0. So this whole part will be 0, I equals to 0. So graph starts with I equal to 0. And then after, as time will increase, as this angle increases in first two quadrants, first and second quadrant, the sine function remains positive. That's why this positive multiplied by negative will remain negative. That's why I is negative, okay? And then after, as this sine function value, I mean this angle value becomes when this time increases and when this angle enters in third and fourth quadrant, at that time sign function is negative, minus minus plus, minus minus plus. So I value will become positive. Okay, fine. Now tell me, I equals to minus q0 omega 0 sine of omega 0 t, same formula written here. But suppose if you are talking about maximum value of I, let it be shown by symbol Im. How would you get maximum value? Very simple. Just write here Im, that is maximum. Then right hand side also must be made maximum. For that maximum value, just put this angle pi by 2. Then sin pi by 2 will be 1, which is 1 means what? Maximum value of sine function, correct? And 1 into minus q0 omega 0, that is minus q0 omega 0, which indicates Im, that is maximum value. So maximum value of this current is this part, let it be Im, fine. And minus Im sine of omega 0 t. I equals to minus Im sine of omega 0 t. This is the current through inductor at the end of t time. Now tell me, when there is a charge on capacitor, meaning thereby one plate is having some positive charge, another plate is having some negative charge. Tell me, one plate is positive, another plate is negative. Then between these two unlikely charged plates of a capacitor, in the space between them, come on, there exists electric field from positive plate to negative plate. And in that electric field, energy is stored in the form of electrostatic potential energy. The formula is this: U equals to, studied in third semester, U equals to 1 by 2 q square upon c. U equals to 1 by 2 q square upon c. Fine. And in the first chapter you have studied, when current is passing through inductor, it develops magnetic field, and in that magnetic field, energy is stored in the form of magnetostatic potential energy. The formula was UB equals to 1 by 2 Li square. Fine. Now you just talk regarding the amount of charge and amount of current, how they change with respect to time from these two graphs. Let us take this much time interval, 0 to t by 4, correct? In this much time interval, what happens? That this charge on capacitor goes on decreasing. Naturally, when this charge will go on decreasing, come on, this electrostatic potential energy will decrease. But in the same time interval, you can see current is increasing. When current through the inductor is increasing, when this current is increasing, naturally magnetostatic potential energy will increase. So when energy in capacitor decreases, energy in inductor increases. In the next equal time interval, what happens? Look, from t by 2 to t by 4 to t by 2, what happens? Charge on the capacitor increases. When charge on the capacitor is increasing, naturally electrostatic potential energy in the capacitor would increase. And in the same time interval, the current through inductor decreases. When current is decreasing, come on, this magnetostatic potential energy will decrease, correct? So when electrostatic potential energy increases, then magnetostatic potential energy decreases, correct? I mean to say here, for the first quarter of a periodic time, during first quarter of a periodic time, the amount of charge is decreasing here and the charge is flowing in this direction, correct? Then what happens? In the next equal time interval, the amount of charge is flowing in just opposite direction. Earlier charge was flowing this way, then this way, then this way, then this way. So direction of flow of charge gets altered at the end of this time interval. What I mean to say, when direction of flow of charge is getting altered, here it gives rise to oscillations of charge, oscillations of charge. And as the charge is oscillating, there are changes in the value of charge, there are changes in the value of current. That's why there are changes in the electrostatic potential energy and magnetostatic potential energy. When electrostatic potential in the capacitor decreases, magnetostatic potential energy in inductor increases. And speak reverse, when electrostatic potential energy in the capacitor increases, then magnetostatic potential energy in the inductor decreases. So there is a transfer of energy from electrostatic potential energy to magnetostatic potential energy. Under ideal conditions, these oscillations would continue for infinite time, and then these oscillations will continue like this only. Energy will get transferred from one form to another form. But in practice, you know what happens in practice? As this charge is oscillating, in this LC circuit, it is performing actually an accelerated motion. And it was Mr. Maxwell who had proved one very important result. Whenever any charge performs an accelerated motion, it emits energy out of it in the form of electromagnetic waves. So from this circuit, actually energy is emitted outside in the form of electromagnetic waves. And because that energy has emitted from this circuit, the energy of the circuit goes on decreasing. If electrostatic potential is stored in capacitor, magnetostatic potential is stored in inductor, go on decreasing, then that decrease in energy is transferred into radiant energy, that is energy associated with emitted electromagnetic waves. As long as there is electric field here, as long as there is magnetic field here, some energy is stored in this circuit. That's why we call it tank circuit. The way water can be collected, water can be gathered, water can be stored in a tank, same way here energy can be stored. That's why in looking to that similarity, this circuit is called tank circuit. LC circuit is also known as tank circuit. Okay. Come on, my dears. Let us go for last two topics now. Come on. What is the electrical power consumed in RLC AC circuit? Let us talk about that electrical power. First of all, we define instantaneous power. Let it be shown by symbol P dash. Instantaneous power is nothing but instantaneous voltage multiplied by instantaneous current. Formula of alternating voltage is V equals to Vm cos of omega t. Formula of alternating current is I equals to Im cos of omega t minus delta. Fine. Now come on, can I rewrite this way? Vm into Im into cos of omega t into cos of omega t minus delta. What I have done now? I have multiplied by 2, I have divided by 2. Can I do that? Yes. Now Vm into Im upon 2 as it is. There is a formula in trigonometry. 2 cos A cos B is nothing but cos of A plus B plus cos of A minus B. 2 cos A cos B is nothing but cos of A plus B plus cos of A minus B. So cos of A plus B means this plus this, omega t plus omega t, 2 omega t minus delta, plus cos of A minus B, this minus this, come on, omega t minus omega t will cancel, minus minus plus delta. Fine. Now tell me, in this formula of instantaneous power, all the values are constants except time. Okay? But when time changes continuously, this instantaneous power will also change continuously. Now that power which goes on changing every instant cannot be measured in practice. That is why we require to define that sort of power which we can measure. Such a power is known as average power or real power, because we measure it in reality. That's why we call it real power. Now that real power is the average value of power over one periodic time. Then for that, what you should do, you should take the summation of instantaneous values of power in one periodic time interval, and then that summation should be divided by same time interval, that is capital T. Let us find out that now. 1 upon T I have taken separately. Now integration of P dash dt means integration of this, means integration of this, but in that this much part is constant. Let it be outside, Vm Im upon 2, and now integration of this I have written here, integration of cos of 2 omega t minus delta dt plus cos delta is constant, integration 1 dt from 0 to capital T, from 0 to capital T, correct? Now this Vm Im upon 2t as it is. And now tell me, integration of cos of 2 omega t minus delta dt, don't you know earlier we had discussed the summation of instantaneous values of cosine or sine function values over one periodic time comes out to be 0. So this part is 0, correct? 0. Plus cos delta as it is, integration 1 dt is t from 0 to capital T. Now this part as it is, and cos delta as it is, and you should substitute the limits now. Upper limit is capital T, after putting minus sign lower limit is 0, t minus 0, that is t. And now this t will cancel, correct? Now Vm Im, I have written here Vm into Im. Cos delta is also written, but instead of 2, I have written root 2 into root 2, root 2 into root 2, correct? Now everybody knows that Vm upon root 2 is nothing but Vrms, Im upon root 2 is nothing but Irms into cos delta. So this is the formula of real power, P equals to Vrms into Irms into cos delta. Now if this cos delta is 0, then this power is 0. If cos delta is 1 means maximum, this power is maximum. So I mean to say value of power is governed, controlled by this factor. Which factor? Cos delta. That's why that factor is known as power factor, by the value of which the value of power is governed, controlled. That's why we call it power factor. Fine. Now let us discuss about values of power consumed in different AC circuits. First of all, we take that AC circuit in which only resistor is present. Come on, what is the formula for phase difference between voltage and current? Delta equals to tan inverse of XL minus XC upon R. But when you say that only resistor is there, meaning thereby inductor and capacitor are not there, so XL is 0, XC is 0. Come on, XL and XC both are 0, 0 upon R, that is 0, tan inverse of 0 will give you 0. So delta equals to 0. Just put it here. When delta is 0, cos 0 is 1. 1 means maximum value for cosine function. When this is maximum, this power will be also maximum. That's why I am writing P maximum. And that equals to Vrms into Irms. Vrms into Irms. So remember, in that AC circuit in which only resistor is present, maximum power is spent. Maximum power is spent, maximum power is consumed. Okay. Now let's go for second type of circuit in which only inductor is there in AC circuit. Okay. You know formula of delta, tan inverse of XL minus XC upon R. Only inductor is there, so XC equals to 0, R equals to 0. Now positive number divided by 0 will give you plus infinity, and tan inverse of plus infinity gives you plus pi by 2 radian. So delta is at present plus pi by 2 radian. Put it here. You know cos delta. Delta is plus pi by 2. Cos pi by 2 is 0. When cos delta is 0, put it here. When this is 0, naturally power consumed is 0. Now tell me, when you talk about half cycle of alternating current, you can say time is changing from 0 to t by 2. This time is t by 4. From 0 to t by 4, current is increasing, and from t by 4 to t by 2, current is decreasing. During increasing current, you know what happens? Inductor fetches more and more current from the source, and that is how more and more magnetostatic potential is getting stored in an inductor. So during increasing current condition, inductor receives energy from the source. And then during decreasing current condition, that energy is delivered back to the source by inductor. During increasing current condition, inductor receives the energy. During decreasing current condition, inductor loses that energy. So, net amount of energy spent in such circuit is 0. When net amount of energy spent is 0, naturally power also will be 0. That is why power is 0. Fine. Then we go for only capacitor. If only capacitor is there in the circuit, then you know formula of delta equals to tan inverse of XL minus XC upon R. Only capacitor is there. So, these two values are 0. Negative number divided by 0 will give you minus infinity. And tan inverse of minus infinity will give you minus pi by 2 radian. When delta is minus pi by 2, again cos delta will be 0. When you put delta equals to minus pi by 2, cos of minus pi by 2 is also 0. When cos delta is 0, power P also will be 0. Power P is again 0. Now tell me, how power is 0? I am showing you. During increase of voltage across capacitor, more and more electrostatic potential is getting stored in the electric field because it is the charging condition. During decreasing voltage condition, it so happens that electric field loses that energy because the capacitor is discharging. I mean to say, during increase of voltage, capacitor gains energy from the source. During decrease in voltage, capacitor loses same amount of energy. I mean to say, effective or net amount of energy spent in the circuit is 0, and that is why the power is also 0. Now, have you noticed one thing? In case of only inductor or only capacitor, current is flowing, but power is 0. Current is flowing and power consumed is 0. Such a current, during the flow of which power spent becomes 0, such a current is called wattless current. What is it called? Wattless current. Fine. Now, let us consider that sort of circuit in which RLC, everything is connected in series. Come on, for such a circuit, earlier you had studied the analysis of such circuit, and in that phasor diagram was like this, in which resistance was shown on the real axis, XL was shown along positive axis, XC was shown along negative axis, and then XL, if it is greater than XC, if XL is greater than XC, then XL minus XC you will get it on the positive axis, and that XL minus XC are shifted here. Okay. So, this much is the value which is XL minus XC. Now, if you just show this point, say by symbol capital H, it indicates hybrid point, and if you join that point with the origin, then this line segment, this much value, this much length will give you magnitude of complex impedance. Distance of hybrid point from origin gives us magnitude of complex impedance. Come on. Here is current phasor along positive x-axis, current phasor, and here is voltage phasor, and phase difference between voltage phasor and current phasor is this much, which is delta, angle is delta. Fine. And now tell me, if I want to find out say cos delta, what will it be? Adjacent side to delta divided by hypotenuse. Come on, adjacent side to delta is R divided by hypotenuse, that is opposite to right angle, that is mod Z. R as it is, can you recall formula of mod Z? Under root of R square plus XL minus XC whole square. Now tell me, if XL is greater than XC, this value will be positive. If XL is less than XC, this value will be negative. Whether this value is positive or negative, but square will be positive. When you add positive value with R square, the answer will be greater than R square. For a value which is greater than R square, if you take its square root, it will be greater than R. Greater than R means what? Denominator will be greater than numerator, ratio will be less than 1. If cos delta is less than 1, then power consumed will be less than maximum power. No doubt, cos delta value is less than 1, but certainly greater than 0, When cos delta is 0, power is 0. When cos delta is 1, power is P maximum. So, at present value of cos delta is between 0 and 1, that is why power consumed is also between 0 and maximum. So, now let us take one special case in such a circuit where R, L, C, everything is present. But suppose resonance takes place. If resonance takes place, then at the time of resonance, you know, imaginary part of complex impedance becomes 0. Imaginary part of complex impedance becomes 0. So XL minus XC becomes 0, meaning thereby XL equals to XC. If XL equals to XC, then this will be 0. 0 upon R would be 0. Tan inverse of 0, that is delta, equals to 0. Once delta is 0, then cos delta, which is called power factor, and delta is 0, cos 0 is 1. So at that time power factor becomes 1, and if power factor cos delta is 1 means maximum. For cosine function 1 means maximum. So power consumed will be maximum, say P maximum. So at the time of resonance, power consumed is maximum, which is equal to V RMS into I RMS. Got it? Now the last article of the chapter, transformer. Transformer is very important device which transforms alternating voltage from one coil to another coil, whose working is based upon principle of electromagnetic induction, visually mutual induction. How I am showing you. First of all, let us try to understand what is the necessity of transformer. See the necessity. Suppose here we have some electric power station which generates electrical power at voltage V and it delivers current I. This power generated is generated at a constant rate. So P equals to V into I is constant. P equals to V into I remains constant. Now tell me, suppose very far from this station we have consumer. The consumer consumes that power. He would certainly use that power for running some appliance, and whatever is the resistance of that appliance, it is called load. This load is called receiver because it receives the power. This power station, because it transmits the power, it is called transmitter. Between transmitter and receiver, if the distance is very large, then in order to deliver that power at a very distant place, we have to install, very long cables. So because these cables are very long, their resistance is also very large. And if resistance is very large, then power wasted in the form of heat, that is I square R, that is called Julian power, will be also very large. That wasted power I have shown by symbol P dash. Generated power is P, wasted power is P dash. So here net power available at the receiver end will be P minus P dash. Fine. What we should do? If this wasted power is more, then ultimately it gives you lot of loss of energy. So what we should do? We should try to minimize that heat loss. Okay? To minimize this wasted power, what we should do? See here power of R is 1, here power of I is 2. So if you somehow can decrease this current, then because here it is I square, then that would decrease the wasted power considerably. In order to decrease current, now come back here, this product remains constant. If I want to decrease this current, then I have to increase this voltage. So we require that device which can increase the level of voltage at the transmitter end. Suppose we have increased the voltage level from 230 volt to suppose 100 times in this, that is 23,000 volts. Suppose if this becomes 100 times, this will become 100th part, 1 upon 100. So instead of I, you may write here I upon 100. I upon 100 square will become 1 upon 10,000. 1 upon 10,000. I mean to say this wasted power will be reduced considerably. Okay. But then what is the problem? If you transmit such a power in which voltage is very high, say 23,000 volt, then what about the power at the receiver end? In the power at the receiver end, you will have very high voltage 23,000 volt, but all our electrical household appliances, they are operated at a very low voltage 230 volt. So what is requirement now? at the consumer's place, at the receiver end, we should decrease that power again to 230 volt. So, at receiver end, you require that device which can decrease the level of voltage. At the transmitter end, we require that device which can increase the voltage level. At the receiver end, we require that device which can decrease the voltage level. And that device itself is known as transformer. If you use step up transformer, it would increase the voltage level. If you use step down transformer, it would decrease the voltage level. Okay. Let us see now construction of this step up or step down transformer. Construction is very simple. We just take isolated soft iron rectangular strips, and they are electrically isolated by just providing a layer of some non-conducting substance over each of the strips, and we just prepare a bunch, and over that isolated bunch we just wind isolated thin copper wire at both the sides, both the opposite ends, and thereby we prepare two coils. One coil across which AC source is connected, it is called primary coil, and opposite coil across which we connect load, we connect some appliance, that coil is called secondary coil. P stands for primary, S stands for secondary. Fine. Now let us see the working of this device. Working is very simple. When you switch on this AC source, it would deliver alternating current which passes through this primary coil. Because of passage of current, here magnetic field is generated, and because the soft iron medium is present having very high permeability, it will so happen that majority of the magnetic field lines will also pass through secondary coil. That is how maximum magnetic flux is linked with this secondary coil. Fine. But here the current in the primary goes on changing because it is alternating current, and depending upon that, magnetic flux of the secondary coil also will go on changing continuously, and because of continuous change in magnetic flux, you will have continuous production of induced EMF across these two ends, and that is again alternating. So this is a device which delivers alternating current from one coil to another coil with the change of voltage level. Either it increases the voltage level or it decreases the voltage level. Such a device is called transformer, correct? This is the circuit symbol for showing step up transformer, in which number of turns in primary coil is less, and here number of turns in the secondary coil is more. If reverse is the case, then it is called step down transformer. These three vertical lines indicates the presence of iron core, and such a transformer in which at the center we find soft iron medium is known as iron core transformer. Fine. What is the theory behind the working? Very simple. Total magnetic flux linked with any coil is directly proportional to total number of turns. If phi is proportional to n, then phi s upon phi p will be equal to ns upon np. Once again I repeat, P stands for primary, S stands for secondary. Find out phi s from here, transfer this phi p in the numerator here, and now take minus d by dt on both the sides. Minus d phi s by dt, ns upon np is constant, minus d by dt of phi p. According to Faraday's law on electromagnetic induction, you know E equals to minus d phi by dt. So this minus d phi s upon dt will give you Es, that is voltage in secondary, ns upon np as it is, this will give you voltage in primary. Fine. Find out Es upon Ep. It would be ns upon np. Fine. Now when we talk about ideal transformer, there is no loss of energy, and because there is no loss of energy, whatever power you supply in the input, that is in the primary coil, same power you can expect in the output, that is in the secondary. So power supplied is equal to power obtained. Come on, power supplied in primary is equal to power obtained in secondary. What is the power supplied in primary? It is Ep into Ip. Power obtained in the secondary coil is Es into Is. Now find out Ep upon Es. Ep upon Es. It would be Is upon Ip. Fine. Now what is called transformation ratio? Transformation ratio is shown by symbol small r, ratio of number of turns in secondary coil to the number of turns in the primary coil of a given transformer is called its transformation ratio. If this transformation ratio is greater than 1, then number of turns in the secondary coil would be greater than number of turns in the primary coil. Such a transformer is called step up transformer. And if R is less than 1, then number of turns in the secondary coil would be less than number of turns in the primary coil. Such a transformer is called step down transformer. Step down transformer. Fine. Just a very small point regarding eddy loss. See, you have studied in the chapter number 1, whenever the magnetic flux linked with some solid conductor goes on changing with time, then that produces eddy currents within the material, and because of flow of eddy currents, we have to suffer heat loss. Such a heat loss is known as eddy loss. What is it called? Eddy loss. If you want to minimize that eddy loss, what you should do? You should use here core, not in a form of a single substance, but in the form of separated, isolated sheets made up of soft iron. Again, we just provide insulated layer over it, and then we prepare a bunch, and when you do that, the effect of eddy currents has been minimized, and that is how we can just minimize the eddy loss. Okay, thank you.